Due to technical difficulties, we are joining the program already in progress.
So they called me up, they're like, Mansour, we need to do this much easier, much faster. Can you tell us a new way to do that? And we were very lucky to come up with the JavaScript application KPI with some new capabilities that I'm going to show you what it's all about. So first, let me show you the application in motion, and then we'll be able to then see what's going on. So this is actually aggregating about 1 million New York City taxi data records. And what I want to do is I want to go over time slide it, and see the heat map of this information in here. So, okay, I can take it and I can now start sliding it and go back and forth behind it, which is pretty cool. But what makes it really neat is when I flip it to 3D, right? And now I can take the time and start having this real-time effect going on. Isn't that cool? I love this thing. And now that gives me the heartbeat of the city, if you think about it. And I can have different criteria by having it a surface mesh. And that's actually what they were going after. And look how beautiful and expressive is this thing in here, where you can really do some really beautiful visualization of massive amount of data that we aggregate. So what we're going to be spending some time in here is deconstructing how I did this, and how, more importantly, you can do the same thing too here. I showed this as a video to a customer one time, and they like, I had it on autoplay, and they were like, wait a minute, is this a video that you're showing me? And I said to them, no, this is the real thing. And by the way, here's the URL. All of you can try it out up there. And more importantly, which is even better, all of it is on my GitHub repo. You can go download it all, and you too can do this thing. Okay, so this session is about deconstructing this process in here, and we're going to go by detail on how you guys can do this thing. And of course, Adam is going to later show you how this is going to become part of, hopefully, as an experiment, part of the product itself, maybe later on. Again, maybe, but this is kind of, it gives you an idea of where we're thinking to do this idea in here. Okay, so let's go back to the code. I know I said no PowerPoints, but this is taking advantage of the new JavaScript API capability that we just released. Actually, 4.3 is out right now. This is based on 4.2, but it doesn't matter. Taking advantage of this one little function here called external renderers. External renderers is a way of extending the ArcGIS scene, 3D scene, with your own WebGL code. Basically, you can add your own code in here to drop down to the display engine itself and take over and complement the current scene that we have. And this is a very powerful thing, and that's what enabled me, this little utility here, to be able to do that, to do that. Very powerful, very beautiful, despite that, despite it is labeled experimental in the web interface, in the documentation. I think I have a feeling that's going to stay for a while in there. Okay, so let me start up with a little bit of fundamentals with you guys. Let's go back to the real beginning of how things are going to happen, and we go from there. So WebGL is basically the foundation for all new modern web browsers, and it's built into it. Why now? You can take your code, a lot of the visualization is actually running in the GPU. Actually, the new JavaScript API, all the new layers that we have, all the symbologies, a lot of the lines, the polygons are all going to be rendered in WebGL directly, and they're working very, very hard on it. And that's why the new hook to it is making it very nice. So WebGL is a rasterization engine, and it does nothing but draw very simple things. Points, lines, and triangles. Actually, it doesn't draw polygons, drawing triangles. That's it. It's very simple scenario in there. But you provided two functions. Those functions in WebGL parlant are called shaders. And there's two types of shaders that you give it. The shader is called the Vertex shader and the Fragment shader. I'm going to talk to you guys about it a little bit. And you write shaders in a language called GLSL, which stands for the WebGL shader language. And it's like C. It's not truly C. It looks like C, and we're going to defragment. The combination of a Vertex shader and a Fragment shader together is called a shader program. Okay, so what we're going to be building right now, when we pass down to this external function, we're passing down a shader program that is made up of those two components in here. Now, the shaders, what makes this thing so powerful is because the shader runs in parallel on all the screen in the GPU. So when they say you have this GPU that can run thousands, or they have 4,000 cores and stuff like that, well, that's actually what they're doing. You're running in parallel all these shaders. And basically the Vertex shaders, very simple. Vertex shaders tell you where to position a particular, where to place a particular point, line, and polygon in the graphic unit space. And a fragment shader, ladies and gentlemen, a fragment shader tells you how to color code the pixel. So let me repeat. Vertex shaders tell you where the pixel that needs to be color coded, and the fragment shader color codes that pixel the way you want it to do that. And how the program gets executed using two special functions that I'm going to be talking about called draw arrays and draw elements. Okay? Now, how do you deal with this data? So there is a way to deal with GPU data and CPU data. Actually, what you have to do a lot, and actually what we're going to be seeing here, is you're going to have to take data from the CPU land and move it to the GPU land. And now I'm diving deep, guys, okay? And how you do that is we do that through something called buffers. Buffers are binary array where you fill them up on the CPU side and you transfer them to the GPU to be executed. So there's this concept of buffers. Now, how the buffer moves and how you pick up data from the buffer is with a variable called the attributes. It tells the GPU how to render a particular buffer information. Now, there's some global variables in this shader program. For example, the projection matrix and stuff like that. Because they're constant, these variables are called uniforms. And you put in them things like, as I said, the projection matrix, the view matrix, and stuff like that. And finally, you need to pass information between the vertex shader and the fragment shader, and you do that using variables called varying in here. Again, so I know it's very quick, but there is this beautiful web page. I highly recommend that we're gonna go through it in here. I'm not gonna reconstruct it all in here. I will highly recommend that you spend some time on it, and I'm gonna dive into it a little bit together to show you how we're gonna be building a program to do that. Okay? So I'm gonna switch literally to it, and I'm gonna show you this thing in here. And I will love you guys to do it. And this is where basically I started. Remember I told you I'm doing a Vulkan mind meld with you guys on how I did this thing? This is where I started to show all these things in there. And this is here, ladies and gentlemen, is a vertex shader. There is that special variable called GL position. That's a special variable that's available there that you have to constantly set. And this is set in parallel. That enables you to place a pixel at a particular location. Now, there's some extra code in here. I'll let you go through here. But I want to show you the other shader, which is a vertex shader. Just like in the fragment shader, there is a GL position, which is a special variable to tell you where to place a particular pixel to color code. There is yet another special variable called the GL fragment color that tells you how to color code the pixel. Okay? So now you know where to position the pixel, and through that vertex, through the fragment shader, you tell it how to color the pixel. Isn't that amazing? So you just have to program those two functions. And actually, what I've done is this is the foundation for it. So everything what we're going to be doing here and we're going to be talking about is building on how to fundamentally set up that GL position and that GL fragment color. Literally, it comes down to those two functions. So everything that we're going to be building is based on that in here. Now, what makes it so exciting is you don't have to define everything. I'll let you go through this whole thing in there, and you literally end up coming down to setting up attributes, moving vertex shaders, moving vertex positions, and all that stuff, and rendering it. Now, let me take you to the other page that he has in there that describes it, that you can go through the code of it to show it to you, but he has a beautiful example of how it is explicitly working. So here it is, ladies and gentlemen. Okay, so you pass in world coordinate if you want to think about it, and the vertex shader in parallel will tell it what pixel to fill. Okay, and imagine doing that all in parallel on all the GPU cores that you have. And no, I know it's doing it sequentially here. This is for illustration purposes, but imagine this thing happening all together. So what you're supplying, ladies and gentlemen, we're going to supply it the left-hand side array, which is basically world coordinate, and it is going to get translated into pixel coordinate. Now, what is the exciting part about the whole thing? Let me show you the Vertex shader in here, how it works. He has a beautiful documentation. Again, in parallel, we supply the edges pixels. That's it, the edges pixels, and we tell it the edges colors. And the fragment shader will go ahead and will fill in the gaps for us. And we'll do that, of course, in parallel. And notice, by just giving the vertices, edges, colors, it linearly interpolates the color in the triangle for you. So it's not your job to fill in the individual pixel in the triangle. You just give it the vertexes colors, and automatically it will fill in the surface for you. And of course, this is a beautiful example here, but it's doing it all in parallel. So again, once we supply these shaders this way, we let the GPU deal with all that stuff. Right? So that's what makes it. So the whole thing, what we're going after right now, again, is composing these two fragments, these two shaders. And once we fill them in with the correct variables, it will then render all that stuff in there. So now we're building from little triangles. We're building this huge mesh. Okay? And that's what actually it all comes down to, is literally taking a small little problem and expanding it all the way out in here. So okay, so that's where we are right now. So I highly recommend, if you have 2 minutes, to go through these things. Now, yet another function that the folks in the JavaScript API gave us, which is, Mansour, how do I turn world coordinate into shader coordinate in such a way that will happen? And this is very tricky, especially when it comes down to 3D, because depending on where the camera is on the scene, that pixel position is going to change totally based on the camera position. Turn out that in the API, the folks in there gave us a helper function, and that other function is a lifesaver, at least for me. I don't have to go around calculating matrices and projection matrices and all that stuff. What they've done is they gave me a helper function that, given a camera position, I can give it world coordinate. What do you mean world coordinate, Mansour? In WGS 84. I give it coordinate in WGS 84. Given where the camera position is, it will tell me exactly the pixel location where I need to feed in the vertex shader at. Isn't that amazing? So this is gold for me, because if I had to do this all by myself, man, it would have been miserable. But having that function in there, and thank you very much, the guys in Zurich that implemented this, man, it made my life easier. So suddenly you can say to me, wait a minute, if I have WGS 84 data and I have this function here and I know how to render triangle, Mansour, wait a minute, your rest of the job is easy. Exactly. And so now we're building on those little blocks. So we're building from little triangles to having a function that turns world coordinate, WGS 84, into pixel coordinate. And so now it's a matter of nothing but filling in the mesh. Isn't that cool? Okay, and the mesh is nothing but, guess what? Nothing but bunch of triangles. That's what it is. So everything in WebGL land is bunch of triangles when it comes down to filling it. And so the idea now is taking that, filling it, creating a mesh, and now what you do is you color code every single mesh vertex by its weight. What do you mean by that, Mansour? This is what I mean by that. So given an aggregation of data points at a particular location, for example, in my case, New York City taxi pickups, right? If at that place at that time, there's a lot of New York City taxi pickups, I will then, using a kernel function, I can weigh all the vertices around it based on a particular criteria. Now, that weight, I can translate it into a color, which goes into the fragment shader, which gives me now the mesh color beautiful scheme. And if I apply a kernel function around that circle in here, then I can have this beautiful, beautiful little gradation that comes on with it that gives me that beautiful surface. And of course, if the mesh is tighter, then the kernel applies on multiple vertices together, gives me a smoother surface. Does that make sense? So now it comes down to now taking the points, finding out where the closest vertex is, looping through all of them, weighting them by the kernel value based on the density of the data underneath it, and then letting the GPU rip to render it. And as I move through time, that whole mesh, think about it, is three-dimensional coming up on the screen, right? And I can now step through time through these multiple meshes. Isn't that cool? Okay, and guess what? You all can do this. This is not difficult. So we started with the fundamentals of what a shader is, and based on that, we build it for triangle. From triangles, we build meshes. From meshes, we weighted the mesh based on the value, and then we made it multiple mesh values on top of it that gives us the three-dimensional aspect of it. And the JavaScript application now is playing through these meshes in space and time to render that application, and that's what gives us that beautiful effect here that we're seeing, right? So when we go back here, what is happening is you can see now, like, aha, of course, Mansour, it makes perfect sense here. Look at what you're doing. But you're saying to me, I don't see it. Yes, so what I did is I made a place where there's no data, quote unquote, transparent. So actually there is a mesh here that is straddling all of Manhattan, but because the vertex at that location where there's no data is transparent, I can see right through, and anywhere there is data, I elevate it and I give it a color proportional to the height. Isn't that cool? So now it's a matter of just deconstructing the code from that, and that's why, and when I step through the time in here, I am projecting different values at that mesh, and I'm elevating them and coloring them according to their value of pickups of data underneath it. Okay? That's what literally it is. So we went from pixel to triangle to multiple triangles to three-dimensional triangles, and voila, that's how we can render this. Isn't that cool? Again, you all can do this. Let's deconstruct it furthermore. Okay, so what I want to show you now, we're going to jump into some code. Okay, and I told you, this is the code. So actually, you can go clone that project, by the way. Again, you can get it from my GitHub repo, clone it, have fun with it. And then that's the whole point, is we're going to deconstruct it. Now, the project is made up of two sub-projects. The project is made up of two sub-projects. One sub-project, which is the JavaScript application using the external render to render the data. But there's another sub-project in there, which is the data preparation, right? So using ArcGIS Pro, because we are selling ArcGIS Pro right now, okay, it is easy to extend it with a Python toolbox, because Python is the language to go by, and that's what we're going to be talking in here, that can prepare the data, that will read it from a feature class, prepare the mesh in such a way that we can feed it to the JavaScript application to do that. Now I know what you're thinking, but Mansour, since you're so smart, why didn't you do it as a REST endpoint and query directly the data directly? I'll leave that as an exercise for the reader when you have some time. You can patch my code when you have some time. Okay, so if at 2 o'clock in the morning you have nothing to do, turn the code into a REST endpoint, you can do that. But I argue with you, ladies and gentlemen, something very interesting. Since I wrote the Python toolbox in Python, I can publish it to server as a REST endpoint. Huh? Isn't that cool? So the desktop code through Python became a REST endpoint. I gave you a hint on how to do it, by the way. And it's so easy because the same code in desktop can be published easily to server to become a REST endpoint. Isn't that cool? That's amazing, and that is what makes sticking with the Python language and the framework and the architecture and the platform. You can take something on desktop, turn it into server, and expose it and visualize it. Anyway, again, I'll leave that for you as an exercise for the reader. So we're gonna start up with the toolbox itself that can give us that criteria in here. And again, it's a Python toolbox that I added directly. So you go, when you start up your own project, you can add it, you can go to the folder where you clone the project, add it as a toolbox. And what the toolbox does, it takes a particular input. I wanna show it to you here. Right? Okay, let me expose you better here. Okay, it takes a particular feature class. Now, the beauty about it is any feature class. This is pure Python search cursor. So I can connect to a BDS, I can connect to a geodatabase, I can connect to, even if I exposed a Hadoop cluster through it, I can read in theory the data from it. Well, I have to use it through BDS in here, but I can read the data in here. So that Python toolbox takes a couple of parameters. It takes a parameters where it tells it, given a particular region of extent that you're looking at right now, I want to construct a cell of 100, I want to construct a mesh of 100 meshes where I want the minimum to be 1 point, and oh, by the way, I want you to break up the three-dimensional space into 30 minutes intervals. So it's going to break up my big data here into 30-minute intervals. So it's going to create 30 meshes based on the period that I have, and it's going to create a file called heat.js. Let me show you what this is doing. It is kind of creating a space-time cube, but a la Monsoor. It's not in etcdf and stuff like that. Let's deconstruct it together. And if I keep it small, like 3 meshes, 1 minute, stuff like that, let's generate that guy. And we're gonna go into the code, and I'm gonna show you what I call a space-time cube. Again, not CDF, a la Mansour, but shows you how I deconstructed this guy in there. So here we go. It is going, I have, by the way, in that 1 million New York City taxi pickups, by the way. I'm plowing through them, deconstructing them into these little bins, and 30-minute time-wise, okay? And voila. So look what the mesh produced. So the toolbox creates a feature class, an ephemeral feature class. See I don't know if you can see it in red. Can you see it in red over there, ladies and gentlemen? Good. That is actually the mesh that had created the triangles, by the way. Remember I told you about the triangles? There they are. So of course, this is by 3. If I had it higher up, it will be denser, but that's not the point of this exercise. I want to switch to the code itself and show you the mesh that it got created. So there's the ArcPy in here, and there's the heat map. So let me make it pretty. Come on, here we go. So, but you're saying to me, wait a minute, Mansour, this is an ADM module. Yes, ladies and gentlemen, it produced an ADM JavaScript module because we're gonna use that to be dynamically injected into the JavaScript application. So it became a Dojo module. So what I'm producing is a Dojo module that is dynamically loaded. I know this is like crazy, Mansour. Why are you generating that? Because I can dynamically generate it for that. So there it is. There's the data in here. And at every timestamp, I have, for a particular location, the weight that is associated with each one of those. So this is my JSON representation of space-time cube. And if I go all the way down to the end, come on, if I go all the way down to the end, it gives me the mesh itself, how many rows and columns, what are the indices that are composing it, and ladies and gentlemen, watch here, the world coordinate that make up that mesh in that space. Isn't that cool? So, now that I have the world coordinate, I can use the JavaScript function to turn it into pixel coordinate that the fragment shader can now place at a particular position. And knowing the vertex position and knowing the weight and time where it is, I can color it by the particular way. And if I do that all in parallel by the GPU, I can go back and forth, and this thing is rippling through space and time. Isn't that cool? Okay, and that's how it is. It's very simple. So we're going to deconstruct very quickly the mesh toolbox. Okay, if you're here, you should know about Python toolboxes, right? Okay, if you're here and you don't know about this, then you guys better catch up on this, because, by the way, this is the way to go. This is how we program. This is how we extend. This is how we do things. And again, what makes it so exciting is this is added directly. You can turn this into a geoprocessing task on the server to be able to do that. So the mesh toolbox has a bunch of parameters, the input parameters, the feature class, the number of cells, the minimum count, the intervals, and where I want to dump the data. And the magic happens is in where? Is in the execute function right there, right? This is the meat right here. So it takes the input, takes the value, finds out the current extent where I am at there, and turns around and calls the create mesh. The create mesh knows the world extent and goes through a little loop in here to give me the vertices where they need to be positioned. Once I get all the vertices positioned, it gives me the object location. This is the object that I'm dumping down into my space-time cube. This is one part of the space-time cube which tells me where the mesh is located in here. Now let's go back to the second section, which is creating the data. This is the part where it goes out to the feature class, and I made some little cutesy thing here where I can tell it to construct by second, by minute, by hour, by day, by week. And it uses the Python API search cursor to go query the location, X and Y, and the date. So based on this now, I can now make sure everything is in the current extent, turn it into a space-time cube, then I can normalize the data by calculating the mean and the standard deviation. By the way, you can do a mean and standard deviation calculation on the fly. I don't have to do 2 passes on the data. I have a Wikipedia reference to how, within 1 pass, ladies and gentlemen, as you know, you can calculate mean and standard deviation. And then finally, I normalize all the data. I normalize it all based on 1 standard deviation of the data. Okay, so taking the mean, the standard deviations, now everything is color-coded. The weight of every weight is proportional to the mean and the standard deviation. Again, I'll let you deconstruct all that, but there's the beauty of the code in here, all in Python and amazing, beautiful in there. And finally, once the whole thing is in there, you can then turn it back into a feature class, an ephemeral feature class that is rendered on the screen. Now, once the data is in there, we turn to a second portion of the job, which is the application itself, which is the mesh code in here. Now again, it's a pure classic JavaScript code with the ye olde fashioned index.html. It lines it up. It has the settings, which is on the left-hand side. It has a location for the panel view for the map. And of course, what it does, it calls the main.js. So this is using the 4.2. I need to update this one to start using the 4.3 API. And it is jumping in to call the main routine. The main routine is a required dojo function, right? We all know and love how to do that. Classic dojo. And there it is, ladies and gentlemen, if you see right here. App heat. That is the dojo module that was created by the Python toolbox that is dynamically loaded in here. That's why I did that. That's why I turned it into a required, because now it's brought in directly. Again, that's the exercise for you guys to turn it into a REST endpoint rather to be bundled in directly. Again, I love to see you that exercise for the reader for doing that. Classic dojo scenario in there. And now we come into the fun part. Remember that external render? There it is right there. It is built, we declare a function, we call it the mesh render, and it has 3 scenarios in there. A constructor, of course. It calls the setup function. This is a function that is called by the external render 1 time to set up in there. What it does, it is, ladies and gentlemen, initializing the shaders. Notice here, how I have built into the JavaScript the shader code to do it. I showed it to you earlier. Again, you need to go study it. But this is the shader code built into it that will give me the two special variable, the GL position and the GL fragment that is the foundation. That's what we started with, remember? So this thing here is actually going ahead, initializing these, how they're gonna be used in there. Okay, fine, let's go back. Once this setup is happening, every periodically, the function render is gonna be called. So now, as the frame of the JavaScript application is rendering itself, at every render, what it is calling, it's calling that render function. And in that render function, I am getting the WebGL context, setting the program that was compiled by the Fragment shader and Vertex shader, and explicitly using magic function to render coordinate. That is yet the other magic function. It takes my world coordinate and turns them into pixel coordinate based on where my camera is. Once I do that, I call the render route, I call the draw routine, which renders it on the screen, and I keep telling it, please, next time through, re-render it, and it happens at 60, 70 frames per second, so your eye sees this motion, this ripple in time happening automatically. Isn't that cool? It's wonderful. It's beautiful. It's expressive. It's amazing. And of course, there's the other thing. I'll leave you around it to do your own magic around it, which is pretty cool. Okay. So with that, I just wanted to. Sorry. Oh. What happened? Oh, this is not good. This is interfering with my mojo. Oh, let's try again. Oops. Oh. Let me try another. Let me try another input. Sorry, ladies and gentlemen. Sorry? Oh, the other one is working. So it's this projector that has emotional issues. Okay, y'all move down. Come on down. Okay, sorry folks. And you thought you needed exercise after lunch. Here you go. Yeah, come on down. Okay. Okay, good. Okay. So that's what basically it's all about. And of course, the rest of the stuff, the rest of the code that I have in there is to set up the view, you know, the base map view, setting up the extent, the current extent. And every time I move the slider, there it is right there. Every time I move the slider, I basically update the visuals, which is basically transferring different values to the kernel, and the loop repeats itself over and over again. And it's doing it so fast that you cannot tell the difference, okay? And even changing colors and changing different items and stuff like that, it doesn't matter. So that's pretty cool and it's pretty impressive. And by the way, as I said, you all can do this. Now that you understand the foundation, the fundamentals for it, you all can go get your own data, use that Python, using the ArcPy API, right, to cookie cut it. Or if you want to do it as a REST endpoint, you can do that. But once you have cookie cutted it, you can now plug it into anywhere you want and render in any way you want in there. Okay? And generating those space-time cube, quote unquote, is now fairly easy. There's the Python toolbox for it, and you can run with it. Now, what I'm excited about, I'm in professional services, right? So I can play these kind of games. I can customize and I can fool around and I can give my customer everything that we need. But at the end of the day, guess what? We build products here at Esri, right? And this is such a cool functionality. This is such a cool functionality that we need to bring it part of the product. So here, I turn it to my friend Adam, who's going to show you what we've been working on in the product as potential solution to be able to do some of these things for you guys so like that you don't have to program it. You are number 3. Here we go.
All right.
Take it on.
Thanks, Mansour. So I lead up the real-time and big data aspects of our platform. And so when we're dealing with big data, we introduced at 10.4 the concept of a spatial temporal data store. And the concept of this is something that can span, it's like a geodatabase, but it spans across multiple nodes. Some of the visualization techniques that we've introduced for this at the 10.4 and 10.5 releases is the ability to aggregate data on the fly. And so this is to match the use case of real-time data that's streaming in, where you might not want to run a tool to get an aggregation. You want the data to be aggregated on the fly as new data is appearing. So at 10.5, we have the ability to aggregate by geohash, squares, pointy and flat hexagons, and triangles. We're also indexing by a temporal index, as well as an inverted index on all the other attributes. So what that basically means in non-geek terms is that you can query this data super fast, and the data can be super large as well. So we've got this project called Qbert, which is, okay, that's cool that we did that at 10.4 and 10.5, but what if we actually took those results and made that available in a 3-dimensional space? So right now when you query the spatial temporal data store, you can get back for this start time and then this end time, give me geohashes, that's one technique to aggregate squares or hexagons, and at this level of detail where I'm zoomed in. And what that would give you is a 2-dimensional graphic with density and geohashes distributed across that area that you're looking at for that time frame. But what if we added a couple more parameters to this? What if we added a time interval of 1 and a time unit of hour. And so for this specific time frame, which is a 24-hour period, would get back 24 slices of aggregated data that I could then render back through the client. And so with all the techniques Mansour has been showing on the client-side rendering using our space-time volumes with WebGL, we can employ those same techniques there. So what this looks like is on the left is a traditional kind of 10.4, 10.5 aggregate response that you would get back from a feature service. This is new at the 10.5 release. The feature services, when you work with data that's backed by the spatial temporal data store, now support the ability to aggregate responses back to the client. So if you wanted to render things client-side, you can query the feature service and give it an LOD type, a level of detail type of geohash, and a level of detail, whatever level that you're wanting to get that result back for. And in this case, I'm not even returning the geometries back. I just want to get the counts back for those geohashes. And so you can see DR and DP are some of the geohashes. I have a second level of detail, so I'm getting 2 letters back. And I can see the counts, so this data is fairly large. The first geohash there has 195 million records in it. And so trying to render that back on a client would be a bit silly, rendering that many graphics on the screen. And so the data set that we're actually working with here is from one of our partners, SafeGraph, who provides anonymized cell phone data from basically mobile apps usage that's happening around the world. So this feature service that we're hitting actually has 1.4 billion records in it, not million, billion records in it. And so we can pull this data back super fast and do aggregated responses. Now what's on the right is kind of our R&D effort of, what if we actually rendered this back through multiple time slices? And so what you would get back instead of features would be space-time features. This is just a working prototype of early form of what we might introduce at future releases. And if we did that, then we would get back the time for whatever the first minute of that hour is, and then all of the aggregate results. If I had said to return the geometries, I would get the geometries inside of that array as well. But basically what we're getting back here is an array that represents time slices of aggregated features. And I could aggregate by geohash, square, hexagon, however I wanted to see that. This data can return a lot of data back to the client. So we're also considering supporting a format of protobuf so that we can actually communicate this really efficiently over the line back to clients. So something we haven't implemented in the prototype yet, but something we're considering to minimize the network transit time of getting these responses back to a client. So what I'm going to show you now is an early form prototype of this. This is using a lot of the same techniques that Mansour has shown. And this is data in New York City again. I can see things in a geohash. Let's just rotate this a bit. I can see things in a geohash, or I can see things in triangle indexing. And I can play this back over time and see the distribution of data that's happening around here. These are the different indexes that the spatial temporal data supports. So we can support triangles or even hexagons. So now we can see this in a 3-dimensional space, like we've done before, but now instead of just being a flat 2D map, we actually extrude the value based on the weight value that's coming back. And we also support cylinders as well. And so if we wanted to see this in a view kind of similar to what Mansour was showing before, we have this heat mesh that we can come back here. And so you can see the distribution of mobile app usage across New York City for this space and time. And so what we wanted to do in Qbert, though, is to go a step further and say, what if we actually looked at the geohashes that are happening in here, but we looked at that across a space-time cube. So I'm going to go back to just the first hour. And if I zoom in here, what we'll see is that if I increase the temporal extent here, that we're actually building the space-time cube on the fly. And so what this allows us to do is if new data was flowing in, we would actually kind of, the data at the bottommost level would be the oldest data, and it would kind of sink into the earth. And then we would have new data appear on the top. So if this was real-time data streaming in, we could do that. Again, it's not just about geohashes. We can represent these as a space-time volume that's based on triangles, space-time volume that's based on hexagons or other things as well. And you can see how responsive this application is. So that's just a quick glimpse into some of the R&D that we're working on inside the product. Some of these features might appear in the 10.6 release, but let us know your feedback on if you think these are good ideas to introduce. But this will answer, instead of going through that data prep exercise like Monsoor showed before, as a product we could actually give you a structure and an array structure that you could render through these WebGL techniques, and then also improve layer support in JavaScript over time as well.
Right. So this is a little bit loud. Okay. So this we wanted to show you some of the stuff. Okay, that now you can do if you want out of the box. If you want to start expressing yourself with that, try out the new Python toolbox. And by the way, let me show you the closer section in here.
Flip back over.
Okay. Yep. Number 4. Right. Is it switching? How's that? Yay. Okay. By the way, all this code is available on GitHub. Okay, so you can go download it, try it out yourself, leave us comments on a lot of these ideas and stuff like that. The Python toolbox is there, the JavaScript application is there. I try to comment code as much as I want, but I write very good code, so it's self-documenting, and I'm modest about it, right? Like everybody of you guys here, right? Is that right? You guys write self-documenting code, okay? So I'm in very good company, okay? And don't hesitate to email me or email Adam. This is our email addresses, right? And of course, tweet the session if you love it, don't hesitate. And more importantly, between Adam and I, we have 8 children. So rate this session very well because we have children that depends on good rating, and we need to feed them because our salary depends on your good rating. And I have children that go to school in the snow, so they need shoes. So think about them and think about Adam's children too. So rate this session very well, please, everybody. Okay? So we're open for questions. Yes, sir. At Emrad, sorry, yes, very good. Yes, you're right. Sorry, I tweeted right, guys, everybody. Thank you.
That's his angry Twitter handle, the
yes.
mad Twitter handle.
Here we go. Emrad, thank you, Omar. Yeah, so retweet whatever you tweeted cool about me with that cool handle, okay? So we're open for questions, ladies and gentlemen, and I know we finished a little bit early, but this is cool, and it's not very difficult. I mean, you guys are super duper programmers and smart people. You guys can read this and understand it. Yes, sir.
How do you envision Kubert from a product standpoint building on what you guys already done with spatial temporal and the existing product lines?
So the question was, how do you envision Kubert being integrated into the spatial temporal and the rest of the product line? So the plan is to just have it, we already have aggregation styles on spatial temporal data store, square, hexagon, and this just builds upon that as another layer on top of that, where instead of just getting back one time slice, you can get back multiple time slices. So it's a natural evolution at 10.6 or a future release that we would expose that as a REST capability on the spatial temporal data store and the feature services and map services that make use of it. Within the client application tier, there's still some work to be done about, do we actually create proper layer types and other things within this so that we make it easier to render these things. None of that's committed to at this point, but that's part of the equation as well that we will need to figure out.
You have no questions about the code? I mean, you guys are super duper, it was so literally self-explanatory that you guys have no questions about it? Or I did such an amazing job that you have no question? I think I'll take the second one. All right. Oh, yes, sir.
It would be good to have a small function to kind of change the width or how big the polygons are, the triangles or
the mesh.
Polygons. Yeah, basically.
Yeah.
Because the problem with 3D cubes is that you can't see really any visualization if it's a whole big cube. But obviously, you did reduce the size of the epicenters of every one of these.
Right.
So
right.
It would be nice to kind of as well.
Yeah, I mean, you can control that, by the way, as you saw from the application.
So repeat the question, please.
Yeah, so the question is, can we control I mean, I made it very dense here, but actually, when I can go back to the toolbox in here and we can see, I mean, I can make it as dense as I like and depending on what you want. So if I go back and I densify it at 100 levels, I mean, what you'll have is a finer granular scenario, and now it will become smoother. The surface will become smoother. And of course, I'm still taking 30 minutes here, and I went down to, in certain application, I went down to 2 seconds. So I had this huge space-time cube, if you think about it, and very fine, and the application was still very responsive because why? Because of the shaders. The shaders. That is my ace in the hole, and that external render function, which is awesome. So,
and if you
so
work
it worked out really well.
So that's one level of detail that Monsoor is showing. So if you work with the spatial temporal data store, you can ask it for a level of detail 9 or 22 or whatever you want.
Right.
And when you set it up, you actually specify how many levels of detail you want to support. So based on the zoom extent, it could actually change on the fly as well.
Right. Yeah. So this, as you can see, it's taking longer to generate the data because now it's a finer mesh. But let it now bring it up. Come on, don't make me look good. Come on, computer, make me look good. It is doing something. It is saving mass. That space-time cube is now huge, by the way. Okay, that space-time cube is huge, and I should close all that stuff to. Yeah, see, it's freaking out on me right now. Because it's generating so much. Close all. Here we go. Come on, baby. You can do it. Here we go. Here we go. See? So you can really create a really, depending on level of granularity.
I meant in the web app itself, or the visualization.
Sure.
Not
Yeah. Oh, okay. And what Adam is doing. Yeah, sure. We can play these kind of game. Guess what, Habibi? Exercise for the reader. That's why I made it a GitHub project. So like that, you don't call me. You have the source code. Love you, baby. Do it. You have the source code. Don't call me. You see? That's why I love open source, because I just show the direction, buddy. Okay? You want to do something? Hey, man. Source code is there. Do whatever it is you want with it, you know? I'm moving on. I'm moving on to other things. But I love to see you. No, seriously, Adil, I love to see your feedback on this thing. Maybe we can collaborate. Right, I'd love to do that. Okay, smart people. Smartest people in the room being here all the time. I love you. In a professional way, of course. Don't call HR, okay? All right, guys. Thank you very much for your time, and we'll see you around, okay? Thank you.